So today we are going to start the public key cryptography. We already started one part of this lecture. Um, uh, we have we have introduced the public key cryptography, and we have seen how public key cryptography is using not using one key as in symmetric key or private key cryptography, but we use two different keys, one public key and one private key. We have also seen that the public key cryptography concentrate on two important things, the key distribution and digital signature. There are two types of encryption in this way. Either you use your public key or the other party's public key to encrypt the data, or use your own private key to encrypt the data. If you use the other party's public key, you are using some kind of encryption, and if you are using your private key, you are using some kind of digital signature or authentication. So two different schemes, and we have introduced those two schemes here. We have said that you can use the other party's public key. As we have seen here, we have the public key of destination. We are going to use the public key of the destination to encrypt our data. Then, yes, I'm recording. The public key cryptography. Uh, okay, by the way, I'm trying to finish this lecture for one session. I'm trying to make it in one session, not two sessions, because it is short. It is a short lecture today. So I'm trying to finish it in one session, inshallah. So the key pair here, we have the public key for destination and the private key for the destination. The destination is sending his or her public key to the source, and the source is going to use the public key of the destination to encrypt the data and then send it to the destination, and destination will use her or his private key to decrypt the data back or get the original data. And this is confidentiality. Confidentiality means secure transmission. Another scheme is to use authentication. Authentication means to make sure of the source of the message. Make sure if somebody sent this message, you know that this guy is sending the message, not somebody else, not a hacker or somebody else. This can be done using the private key of the sender. This way, we are using the private key of the sender. The private key of the sender is used in encryption, and then the data is sent through the insecure channel, reaching the destination. The destination is going to use the public key of the sender. And now, if the destination can decrypt this data, he is making sure that this data is coming from source A, not from somebody else. This is authentication. And also we said that we can use both approaches to have more strong scheme that has the authentication and secrecy, or authentication and confidentiality together in one graph, on one algorithm. So we are going to use two pairs of keys, one at the sender and one at the receiver. The sender is going to encrypt two times, one using his private key and one using the other party's public key. Then send the data through the insecure channel, receive, destination is receiving the data or the secure data, and then use his private key to decrypt the data, then using the public key of the sender to decrypt again. So two times encryption and two times decryption. And I have asked you a question last lecture about the problem of this algorithm, and actually you tried to answer the question, but the answer was the complexity. The complexity means I'm using more secure algorithm, but I pay off some performance because this is little complex algorithm. It takes more time. It needs more processing, more software, more hardware if I want to implement it as a hardware. So this is going to cost more hardware or more software. Okay, so the applications of public key crypto system, we have three types of applications. The first one is encryption, decryption, and we have seen how to make encryption and decryption using the public key, the recipient public key, and the digital signature. Digital signature means to make sure of the source of the data, and then we have used the sender's private key to sign the data or sign the message. And the last one is key exchange. And we will see in the next lectures, not today's lecture, in the upcoming weeks, inshallah, we will see how to make key exchange, even for symmetric key. We have seen that in symmetric key encryption, we have a problem of keys, that we are sending the keys from sender to receiver. We have to use, or we have to send the key. But now we can use public key encryption to exchange the keys securely. So maybe this is a function, we are going to use it back in symmetric key encryption, the last one. Okay, and we can cover all the public key crypto systems. Here we have these algorithms. We are going to study all of them. We're going to study RSA in today's lecture, and in the upcoming lecture we are going to study elliptic curve, Diffie-Hellman, and digital signature, DSS. So RSA can be used in encryption and decryption. It can also be used in digital signature. It can also be used in key exchange. Also, elliptic curve can be used in encryption, decryption, digital signature, and key exchange. But Diffie-Hellman is only proposed for key exchange. So Diffie-Hellman is only for key exchange. For example, these are a common problems happens in the examination or the tests. The students think that RSA, elliptic curve, Diffie-Hellman, all of them are used in encryption and decryption. No, except Diffie-Hellman. Diffie-Hellman is only proposed for key exchange, exchanging the key between the sender and the receiver. So actually Diffie-Hellman alone is not doing anything, but we can combine Diffie-Hellman with, for example, data encryption standard, which is a symmetric key. So we combine it for secure key exchange. So it should be combined with one algorithm uh, to securely exchange keys. Last one is DSS, and DSS is just digital signature. So it is used for digital signature only. It cannot be used for encryption and decryption. It cannot be used for key exchange. So these are the public key encryption types, and we will explore all of them in the upcoming lectures, inshallah. The requirements of the public key encryption. Okay, uh, I'm I'm trying to ask a question here. before continuing to see if you are with me or doing something else. Okay, I'm asking a question. Concentrate with me, okay? So if I want to use public key encryption for digital signature, what will I do? Anybody can answer me? Okay, by the way, I
دك-
might. Okay, okay,
تفضل
اتفضل.
دكتور. لا أقول يعني الريكويرد مكتوبة هني أوريدي.
No, I'm not asking about the requirements. I'm asking about the if I want to make public key encryption to use it as a in digital signature, what will I do? How to make that? I'm not asking about the requirements.
ما عندي فكرة دكتور.
Okay, okay, let me stop. So the public key requirements. Please concentrate with me because after 2 or 3 slides, I will ask you back. Okay, so concentrate with me. The conditions that these algorithms must fulfill is all these conditions, which is 1, 2, 3, 4, 5, 6. Okay, we can say the most three, one or four. Okay, let me concentrate on the most important conditions. The first one is it is computationally easy for party B to generate a pair of public and private keys. So we have to make sure that it is easy for anybody to propose public and private key. If this is difficult, the algorithm will not be possible. This is algorithm for proposing two prime numbers in RSA prime numbers. So it must be easy to propose those prime numbers. And also it is computationally easy for a sender knowing the public key and the message to be encrypted to generate the corresponding ciphertext. So if the sender A has a public key for B and taken this public key together with the message, he is able to generate the ciphertext. He should be able to generate the ciphertext using the receiver's public key and together with his with the message. Then he send the message or the encrypted message to the receiver, which is B, and then B is going to use his private key to decrypt the data. It is also computationally easy for the receiver to decrypt the resulting ciphertext using the private key to recover the original message. This is also should be a condition or requirement. B will be able to decrypt the data using his private key. And the most important requirement here, which is it is computationally infeasible for an adversary knowing the public key to determine the private key. So if an adversary eavesdropping the channel and captured the public key, he will never be able to guess the private key. If using the public key, he can guess the private key, this is not good algorithm. We have to make sure that the hacker will not guess the private key using the public key. And it is computationally infeasible. Also, this condition is important because it is about security. So it is computationally infeasible for an adversary knowing the public key and the ciphertext to recover the original message, even if the adversary know the public key and the ciphertext. It is infeasible or impossible that he can recover the original message. This is very important. The last two conditions are very important because they are talking about the hacker, how we are thinking about the security of our algorithm. And also the last condition here, or the last requirement, is that the two keys can be applied in either order. The first apply the public key and then apply private key, or the opposite way around, which is applying private key, then applying public key. And these are the requirements for making or thinking about the public key as a function. If we think about a public key as a function, it should be a trapdoor one-way function. Trapdoor one-way function is simply, if you know about functions in the mathematical courses, so we have y equal f of x. This is calculating y using x by applying a function f. This should be easy. But reversing this operation is not easy. Getting x out of y is infeasible. So this is one-way function. One-way means it goes one direction. It cannot easily go to the opposite way around. It cannot easily go to the opposite direction. This is the meaning of trapdoor one-way function. It is easy to make y f of x, but it is infeasible to get x out of y using x f minus 1. F minus 1 is the inverse of f. So this should be the one-way trapdoor function, and this is how to describe it. We can re-estimate or not re-estimate, it is restating, we can say restating the conditions in a function way, I mean in a function sense. So we have functions here, and we can describe the conditions here using those functions. So the first condition is what? Y equal f k of x, and k is a key here. This should be easy if k and x are known. So if k is a key and x is the secure message. If I know the key and x, this should be easy to calculate y. And the x equal f minus 1 k of y is easy, and also if k and y are known. This is also easy, should be easy, if k and y are known. But it is infeasible, the same function here is infeasible if y is known but k is not known. That's the most important, because if k is not known, this is infeasible. Shouldn't be easy, or shouldn't be possible. Okay, these are the conditions, and we have set these conditions using the trapdoor one-way function. So about the cryptanalysis, if we think about RSA or public key encryption, somebody may say public key is more secure, means it doesn't have problems, but actually it has many problems. And in the upcoming generation of public key encryption, they try to solve these problems. So for public key encryption is vulnerable to brute force attack. This is the first attack that is public key encryption is vulnerable to. But we have a countermeasure here that we can use large keys. We can stop the brute force attack or making it in not feasible time, like years or thousands of years, if we are using large keys. But actually, we have to make a trade-off because a small, it should be, the key should be small enough for practical encryption and decryption, and it must be also big enough for security, or large just because to deter the brute force attack. So it should be not too small, not too large, not too small because somebody can guess it, not too large to make it to be feasible.
practical.
Yeah, to be practical, exactly. To be practical because maybe if it is too large, it will take too much time for fast applications. If you need to have fast applications, you will not be able to use it. Key sizes that have been proposed result in encryption decryption speeds that are too slow for general purpose use if the key sizes are large. This is this is going to slow down the algorithm. And also, the public key encryption is currently confined to key management and signature applications. That's an addition for public key encryption and decryption. Actually, it is proposed for encryption and decryption at the beginning, then it is confined to be used in key management or key exchange and digital signature applications. Uh, Another form of attack is to find some way to compute the private key given the public key, but actually this is not feasible, this is not applicable, and using the currently processing power, it is not possible to know the private key using the public key. Okay, before starting in RSA, I want to ask a question. Okay, I want to ask a question. Uh, okay. Uh, what is the meaning of a trapdoor one-way function? What is the meaning of trapdoor one-way function? Anybody knows the answer for this question? This is very straightforward question. One-way function. What is the meaning of one-way function?
Does that mean doctor can be operate from one side only,
Yeah.
like
Uh,
the decryption only can, or the encryption
yes. Yes. Can you? Yes, exactly. But can you make it mathematically speak like functions?
function like uh, وين ادور الحين في المكتب دكتور وين نفس بالفانكشن.
دكتور
ممكن تكتب عادي.
دكتور
Okay. Yes.
what I understood, it's like easy to compute in one direction.
Yes. Yes. Exactly. Yes, Abdullah Ahmed. You can calculate x given, or sorry,
True.
you can calculate y given x using the function f, but it is impossible to calculate x
Yes,
using
doctor. Yes,
y.
you're right. That's what I meant. Yes,
Okay.
doctor.
Exactly. Thank you.
Welcome. Thank you, doctor.
Thank you. Uh, exactly that. It is also, Nurhan, hard to invert given the image of the random input. It means that we cannot we cannot get the we cannot get x, which is the input, given the output, which is y. We cannot calculate using f minus 1. F minus 1 is the opposite or the inverse of f. We cannot use it doesn't have inverse. The function doesn't have inverse. This is one-way function. Okay. Okay. Exactly, Hanin. That's correct. Uh, Moving to RSA. The previous slides we were talking about public key encryption in general. All the conditions we have met, all the speaking we are saying about public key encryption in general. But now we are going to speak about the RSA algorithm. We starting from this slide, we are going to talk about the public key encryption, which is RSA. We are talking about RSA. And RSA is developed in 1977 in MIT. It is proposed by the three scientists, which is Ron Rivesett and uh, Eddie Shammer and Adelman. The Rivesett, Shammer, and Adelman, if you see RSA, and RSA, the beginning of the RSA letters, it is extracted from the beginning of their names. And actually, starting from 1977, the they have made a breakthrough. They have made a very change or sudden, or you can say they shocked the entire encryption community using this algorithm. Actually, before that time, nobody think about having a key not transferred between the sender and receiver. Starting from 1977, they start to say we will never send the key between the sender and receiver. We can send public key or public information, and using this public information, nobody can guess the private information. That's why they have proposed this algorithm, just to get rid of the send for the trivial or very insecure method of sending the key between the sender and the receiver. It is most widely used in general purpose approach to public key encryption. So whenever you say public key encryption, you say RSA. For the algorithm itself, it is a cipher in which the plain text and ciphertext are integers between 0 and n-1 for some n. This we are going to propose or see the plain text, how to make it as integers and how to encrypt it. The typical size of n is 1024 bits. This is can be in decimal 309 decimal digits. This simply we can say 2 to the power 1024. This is going to give us 309 numbers beside each other, like decimal number. This is very long decimal number. So RSA is making the expression with exponential. If you see the encryption, how to make the encryption is just using m to the power e mod n, and the decryption is c to the power d mod n. E here is a public key and d here is a private key. So if you know this is public key is E, as you see here, we have pairs of E and N. E is a public key and N is common or public information, and the private key is D. This information D shouldn't be known by the adversary. You can use these two equations to make encryption and decryption. This is the ciphertext, and this is the message, and this is the message, and this is the ciphertext. To make the ciphertext, you take the message, use the public key mod n, then you get the ciphertext. If you want the plain text or the message itself, you can use the ciphertext using the private key of this receiver mod n. Then he can get or she can get the message back. Okay, this is how RSA is used. We can have also the algorithm for the conditions, the same conditions that we were talking about functions here. These three conditions here, they were for public key in general, but not for RSA. For RSA, we can restate them like it is possible to find values of E, D, and N such that M to the power ED mod N equal M. This should be possible. It is relatively easy to calculate M to the power E mod N and C to the power D mod N. Should be easy to calculate, and it is infeasible to determine D given E. If you know the public key, you will never be able to guess the private key. These are the same conditions as previously, but applied only for RSA. Now we go to the calculations of RSA. We select two numbers, prime numbers, and we calculate n by multiplying the two prime numbers, and then calculate 5n. 5n is just simply because these are two prime numbers, they are prime number minus 1. And here the integer e is the public key, and this E should be have the greatest common divisor between itself and the 5n to be 1. We call it co-prime with 5n, co-prime. Then last we calculate D using this congruence equation. D should be congruent with e to the power minus 1 mod 5n. E to the power minus 1 means to have 1, a remainder of 1. Okay, so now we calculated the public and private key. We have seen this in the second lecture, but here we will take it in more detail. The public key is just E and N, and the private key is D and N. We can make encryption using the public key by using this equation, C equal M to the power E mod N, and we can extract or decrypt the data using M equals C to the power D mod N. This is the algorithm, and here numerical example, not for the algorithm itself, but on how, for example, if you want to calculate 88 to the power 7, you can have 88 to the power 7 by simply dividing it to 88 to the power 4 and 88 to the power 2 and 88 to the power 1. 1 plus 2 plus 4 is equal 7. And then you can take each one of them and calculate it separately. You take 88 to the power 1 and calculate it. Then take 88 to the power 2 and calculate it. And then take 88 to the power 4 and calculate it. Then finally, you can multiply the resulting 88, 77, 132, multiply them by each other, and then mod 187 to get 11. This is not actually an, it is not a numerical example. It is just to simplify the exponential, how to simplify it, how to calculate it in more efficient way. Actually, this maybe we will not need this if we have a calculator. If you are using a calculator, you will not need such calculations. And for this example, this is just a numerical example. After calculating the private and public keys, n is 187, and the encryption using the public key here is 7. The public key is 7, and the private key is 23. The private key is 23, and the public key is 7. The plain text is 88 and the ciphertext is 11. We can use these calculations. We have 7 here, mod 88 to the power 7 mod 187. This is going to give us 11. Then we go to the other party or the receiver, the recipient side. Take 11 to the power 23 mod 187. This is going to give us back the plain text. As you see, just using the mod and the exponential, we have this magic, which is the function is reversible. This function is reversible, but not, it is reversible if you know the information, but it is not easy to be reversed if you don't know the information. For example, if you don't know the private key here, if you don't know the private key, which is 23, you will never be able to calculate this or to use this function or to use this equation. That's the magic. Just like as we have seen previously about XOR. We have seen XOR is used in encryption and decryption. Here we have the same effect, which is using the same algorithm for encryption and decryption, but actually with different information. But the same concept, the same algorithm. Okay, so this is how, and this is actually a numerical example. If I want to encrypt how are you, this is a sentence, and how to encrypt it, just simply to make how or H O W, these are the letters, to be each two consecutive numbers should be in less than the n, which is here. N is here 187. So here I should have each two consecutive letters, for example, H O W A R E Y O U and the question mark, taken pairs, pair by pair like that. For example, H and O together is going to give me a number which is 3,314. And here n is what? N is should be large to cover this P1. So in here is what? How to read it? 11,023. So it is 11,023. This is less than 3,000 is less than 11,023. So all of these numbers, which is H O W A R E Y O U question mark, all of these numbers, if we combine them together, they will be less than 11,023. Now we have each consecutive pairs in a number. This is P, which is plain text 1, plain text 2, plain text 3, plain text 4, plain text 5, plain text 6. Now we are going to use the public key and private key pairs. We have the public key, how to create this public key encryption in this part here. This should be done first. This part should be done first. This is the first step here. The first step is to select random numbers and propose private and no, not private, two pairs of prime numbers. So we selected P and Q, which are prime numbers, 73 and 151. These are the two prime number. And using the calculations or the equations before, we find E to be co-prime with 5n. We found 11 is okay, is good a choice. And here, these are the calculations on how to calculate these using the E, which is the public key. We can calculate D, which is 5,891. So we have the public key and D is a private key. And we have N here. And this is how to calculate this N is just to, we have the prime numbers here, 73 subtract 1, 151 subtract 1 and multiply them together. 73 subtract 1, 151 subtract 1 and multiply them together to have these the number here, which is 11,023. Actually this is should be one here, 1,000. This should be 1,000 like that, and this is should be 23, not no, no sorry, it should be 72. Okay, let me make sure of this. I should stop here. I should escape. I just want to make sure if these calculations are true or not, because I see they are not true. Let me open. I know that you don't see the screen. I will share my screen. Now we can use the calculator to calculate 72 multiplied by 150. This is 10,800. Okay, but this is not, this is should be why he calculated 73 multiplied by 51. It doesn't make sense, because he already proposed 73 and 151. This is the prime numbers. Then he subtract 1, 72 multiplied by 150, not 151. This is 10,800. Okay, so multiply it like 73 multiplied by 151. This is even, no, sorry, this is not 73. 73 multiplied by 151 equal what? 11. Oh, okay. 5n. Okay. Now I got this. This is just a small error here. It is a small error, not that big one. The error is just to add 1 here. This is 151. This is n, and this is 5n. That's correct, but here the slide is missing this one. That's that's why I have been confused. Now I have n, I have 5n. I can, using 5n and n, we can get the private key. All these calculations can be done, and then we have the private key pairs, public key pairs. Here, these are the public key pairs. These are the private key pairs. Now, using these keys or these key pairs, we can make the calculations. These are the P's, as I told you about how to divide it to plain text. We have H to be corresponding to 33, and O corresponding to 14, and W corresponding to 22, and so on. After that, we can take the private key here, sorry, to the plain text to be 3,314, and the P2 is the second part of the plain text is 2,262, and so on. After that, after that, we can calculate each block's uh, C, which is ciphertext. How to make it? For example, I have this one. I can use the public key, which is 11 mod n. 11 mod n. Then I will take each one of them and apply the same equation. So C1 is 3314 to the power 11 mod 11,023. This is going to give me 10,260. And I can take this and apply the decryption here. I take this number, which is 10,260 to the power, this is the private key, to the power 5,891 and mod 11,023. This is going to give us 33 back, 3,314, which is the plain text. So I'm applying, the encryption, and after transmission, I applying decryption to get back the same data. Okay. And this is actually at the left side, the general approach. This is just general with symbols, but here to the right is an example, is a numerical example. Okay. Did you understand this? You understand this algorithm is okay?
It's complicated, Doctor, but yeah.
Yes, this is not that complicated, but let me show you. I'll show an example. It is the comp is not actually, this is not too complicated. Actually, it is straightforward if you know the public and private key pairs. You are applying one equation, which is something to the power key, which is something to the power key mod n. Just like that, you apply the same thing in the encryption and decryption to get the information. And this maybe the complicated thing is not the encryption and decryption. This is the creation of the public and private key pairs. This is the most difficult part. You can say this is the most difficult part. This is just straightforward. You have the public key and private key. These parts are straightforward. You can apply the public and private key pairs immediately. But here, how to calculate this, it needs some calculations. It needs some mathematical background about the prime numbers, the co-prime numbers, the greatest common divisor, and many other concepts that you have to remember from previous chapters. But the algorithm itself is straightforward. I don't know if you remember we have taken an example. I don't remember exact example, but I can let you know. We try to make it back. For example, I select two prime numbers p equal p equal, for example, let's take 3 and q is 11. Okay, we are going to use the same algorithm but with different number. Here p equal 3 and q equal 11. N equal what? Equal p multiplied by q. This is n. N equal what? 33. 5n is what? 5n is easy because I know that the root the root values of P and Q is simply all numbers before P and Q. So it's just P not minus 1, P minus 1, multiplied by Q minus 1. Okay, but you keep brackets here. This is simply P minus 1 is 2, multiplied by Q minus 1, which is 10. We have 11 minus 1 is 10. So the result 5n is 20. Now I want to propose the public key. How to propose the public key? I have to get the greatest common divisor of that 5n and the public key, which is E, to be equal 1. What does this mean exactly? It should be coprime. It should be coprime with 20. For example, let us select one by one, numbers one by one. One is not okay. Two, what about two? Two is not okay because it is a prime number, but it is co-prime with 20 because 2 divides 20. 2 divides 20. So it is not okay. What about 3? 3 is not okay because we already selected it. What about 4? 4 is not okay too because 4 divides 20. So 4 is a even number. Even number, they are not prime numbers. Or not important to be prime number, it should be co-prime to 20. What about 5? What about 5? 5 is okay? No, it's not okay. Why? Because 5 divides 20. So 5 is not okay. What about 6? 6 is not okay because it is even number. What about 7? 7. Yeah, 7 is okay because it is a prime number and it is co-prime with 20. It is co-prime with 20. Co-prime means they don't have a common divisor. They don't have common divisor. So 7 is okay. Now I have the pair of the pair. I have the pair of public key pairs, which is PU of 7 and N, which is N is what? Is 33. But now I want to create the private key too. I want to create the private key. How to create the private key? I have to find something multiplied by D, something multiplied by E is congruence with 1 mod 5n. Okay, I will not write 5n because 5n we know it now, which is 20, mod 20, mod 5n, which is 20. Now, what is the number should I multiply it by E, which is the public key, which is 7. Now, remove this and write 7. What is the number to multiply it by 7? Give us a remainder of 1 mod 20. Do you know? Anybody knows? What is the number? I multiplied by 3, sorry, I multiplied by 7 to give me a remainder of 1 after modding with 20. Anybody knows?
7,
This
doctor?
3.
3, exactly.
3, doctor.
3, yes, exactly. So 3 multiplied by 7 is equal to 21. 21 is congruent with 1 mod 20 because after modding with 20 is going to give us a remainder of 1. So now I get the private key, which are PR, private keys of 3 and 33. Now I get the complex one. I get the public key and private keys. Now, if I want to encrypt the data, I am using this equation, which is C equal what? Is equal to M, which is the message, whatever the message is, the integer number. Is okay to have the message as integer number, like ASCII value or something, whatever. M to the power what? To the power public. To the power public. Public is 7 here. Mod, mod what? Mod 33. Now, if I want to get the encrypted text back, which is what plain text is equal to what? Is equal to C mod to the power what? To the power private key, which is 3 here, mod 33. This way I can have the encryption and decryption algorithm. That's it. You can just take the numbers of M. For example, you can represent each number with its position in alphabets. For example, A is 0, B is 1, and so on. You can take all these integers and apply. The algorithm is going to work with you without any problem. Okay? Okay. Okay, let me move to the next slides. We have taken too much time in this slide, but it's okay. This is the core of the algorithm. This slide is very important. This slide is like, this is the key slide. And about the key generation, the key generation, we have to determine two prime numbers, which is P and Q, and select either E or D and calculate the other. You can take E or D and calculate one. Just take one key and try to derive the other. Okay. And the method for finding the large prime number should be reasonably efficient. And if you want to select or to see if a prime number is a prime, is a number is a prime or not, you have to apply this algorithm. You pick an odd integer n and pick another one before n, which is less than n at random. And then using the a and n, you can make a test, primality test. This primality test can be used like algorithm like uh, Miller-Rabin. This is Miller-Rabin is an algorithm to test the primality of a number. You can use both these values to test if n is a prime or not. If n fails this test, you can go back to step 1 and pick another number and pick another random number before it, which is a, and then try it again. If the test fails, then you try another numbers and so on until you find the prime number that you need. But actually, I have here, if you want to read more about the primality test, you can go to this website and see all the tests that make sure that this is prime or not. I think you can see my web browser, right? You see my browser. You can see the website, right?
Yes,
Yes,
yes.
okay. For example, you take a number, say this is large number, and if you see the units of this number is 6, and 6 is even, but even is not a prime number. This is failing this test. So you can say this is not a prime number just because it is an even number. Okay, another example, take a number, say this number is long number. The units is not 0, 2, 4, 6, 8, because if it is one of them, it will be an even number and it fails the test. Then we get the sum of all numbers and take this sum as 27. 27 is not a prime number just because 27, 2 plus 7 is what? Is 9. And 9 is divisible by 3. This means that this number is divisible by 3. So it is not a prime number 2. And so on. You can read all the tests here to check if this is a prime number or not. But actually, I don't want you to get all of these details. I just showed you the idea of testing if this is a prime number or not. This is not easy task. This is not easy task. For example, if you have a number, random number, you you are testing if it is a prime or not. And other approaches, even some approaches do what? They keep all the lists of the prime numbers in a memory. For example, they keep for more than 1 million numbers and test against this list. If the number in the list, it's okay, it's a prime number. If it is not in the list, it is not a prime number. Because it is not easy to say if a number is a prime or not. You can say it because you are a human, but even with large numbers, it is not easy for you to test it, for human also to test it. What about computer? This is a big challenge. So we pick two numbers, we check if they are uh, prime or not, and then we can continue the procedure of making the public and private keys. Now, for the security of RSA, if you imagine that RSA is very strong, no, it is not too strong. They have common attacks like a choosing ciphertext attack. Just if you can you can have a specific text and then apply it to the sender, and then the sender will reply back by the ciphertext of this plain text. You can analyze, you can analyze all of this text and then get out the private and public key values. And the brute force attack is to try all possible keys, but this is not feasible for large prime numbers. The mathematical attacks, this is equivalent to the effort of factoring the product of two prime numbers. So this is mathematical, means trying to, you have the n, which is the public number, n, as we have seen 33, this is public, but 33 is a multiplication of two prime number. If I can have the, to guess the multiplication of, to get that prime number, okay, let me return back. For example, we have seen here that this number is a multiplication of two numbers here, which is 73 and 151. This is, I told this there is an error here. Should be 151. So the multiplication here of these two prime numbers gives the 11,023. 11,023 is public. Anybody can see it. But I can see 11,023, it should be a multiplication of two prime numbers. So the hacker is trying to try all possible multiplication, trying to get two prime numbers and multiply them. If he gets 11,023, so he knows that these are the private and public keys. He can guess the private and public keys. He can continue this algorithm. He can continue this algorithm. But he sees also, he only sees the 11,023. He cannot guess the public. He cannot guess the multiplication. He cannot guess it. Okay, just because it is not easy like that. This is not 11,023. This is very short number. I told you the common number is what? I will return back to this slide. This is very important. 309 decimal values. This is large number. This is very large number. You know how many numbers are there? This is 309 numbers. How many numbers here? This is one, two, three, four, five numbers only out of 309 numbers. You imagine this is, it should be very long number. So here, this is easy. You can use computer to try many possible prime numbers to get the 11,023. But if this number is 309 numbers, digits, this is going to be a challenging task. And the last, the timing attack. The timing attack is talking about the time taken to do something. And using this calculation, if you have very accurate time measure, you can guess the plain text. The factoring problem is just to have to try to guess, as I told you, to try to guess two prime numbers and try to have, if you know the prime numbers, you will be able to calculate 5n and then getting 5n and try to calculate the public and private key pairs. This is just simply to be able to factoring, to factor the n, which is a public number, as I told you in the example, which is 11,023. That 11,023, if the hacker, the hacker can know them, because they are public. He will take, or she will take, the number and try to factor the number to two prime numbers. If he or she can or able to factor the number to two prime numbers, he can be able to continue calculating the public and private key pairs. Now about the timing attack. This is one of the attacks that is, it is not a normal way of attacking. It is to apply some plain text and then apply it to the sender and to the receiver, and the receiver will reply back by the encrypted data, and then the encrypted data can be used to calculate the time needed to decrypt specific text. And using this time, we can guess the public information together with the private information. To calculate the cycles needed to calculate, to count how many cycles in a processor cycles. You know, cycles about the processor. The processor needs some clocks, and that clock makes specific cycles to calculate something or do some job. Using the timing attack, actually it takes it is coming from different angle. It is not expected, as normally we are faced with brute force attack, but timing attack is coming from different angle. So it comes from a completely unexpected direction, and also it is only a ciphertext attack. Means you have the ciphertext, you apply some algorithm to calculate how many time taken to do this ciphertext, and then try to make your own calculations and compare the calculations to guess the public and private keys. This is one of the attacks. The countermeasures of timing attack is to have a constant exponentiation time. Constant exponentiation time means ensure all exponentiations taking the same amount of time before returning a result. This way, the attacker will not be able to guess the private numbers, and he's not able to find or to use the timing attack, because all operations are taking the same time. Also, we can apply or make some random delay. Make a random delay means to apply some delay in processing, not normal. So the calculations for the attacker will not be correct. But you have to make sure that these two calculations or two countermeasures, they degrade the performance. They degrade the performance. Okay. And the last one is the easiest one, or maybe you can say this is the fastest way, or the most accurate way, is just to multiply the ciphertext by a random number before performing the exponentiation. This process is very good and high performance, having high performance to deter the timing attack. Just multiply the initial numbers or the initial integers that you want to encrypt by a random number, and then calculate. And then at the receiver, you do the opposite way, which is divide by the resulting numbers, divide them by that random number. Okay. And last, here we are going to finish our lecture, is to talk about the chosen ciphertext attack. This is one kind of attack that have weakened the RSA